Hey there, I'm going to work a couple examples from our incline force 2. And so I'm going to work number 3 and number 5. Number 3 says we have an object that has a mass of 6 kilograms that's being pulled up a ramp, and that ramp it has a 45-degree angle, and then the tension that it's being pulled up with is 92 newtons. The acceleration is 5 meters per second squared up the ramp, and we're asked to find the friction and the normal force. So um, in the incline force 1, we had balanced forces. Okay, so the object was at rest. Now we're going to start moving into unbalanced forces, where the object is accelerating on an inclined plane. And so to start out, we'll make our free body diagram. Okay, we have Fg going down. Tension is parallel with our ramp. Friction is parallel with our ramp, pointed down the ramp. And then we have our normal force that is perpendicular with the ramp. And so from here, let's go ahead and make our net force equations. We have the net force equation for the y direction, and it's going to be equal to the normal force minus our y component, so FGY. In the x direction, we have tension minus we have two that are going down the ramp. We have our friction and our x component of the weight. So there's my two net force equations. And they're asking me to find the force of friction and then the normal force. So let's start with our normal force, okay? Because vertically speaking, we're balanced, right? We're not accelerating off the ramp, right? We're accelerating up the ramp. And so my normal force then is just going to equal to your y component of the weight. And so if we have the triangle and we draw an arrow down, so there's my FG. So this would be my FGY, and here is my FGX, and then this is the angle theta, which is equal to the angle of our incline, the 45 degrees. So we're trying to solve for the FGY, and that is adjacent to that angle, so we would use the cosine function. So it would be FG cosine theta. And so the mass is equal to 6 kilograms, so that means your weight is equal to 6 kilograms times 10, which is equal to 60 newtons. And now we can just plug in. So your normal force is going to equal 60 newtons times cosine 45 degrees. And if you plug that in, you end up with 42.4 newtons. So there's my normal force. And then we also need to find friction. So when you see that and it's asking you to calculate friction, one of the first thoughts that might come to mind is we have an equation for friction, right? So remember the kinetic friction is equal to the coefficient times the normal force. Now we have the normal force, but the problem didn't give us the coefficient, so we can't find the kinetic friction using that equation for friction. So let's go to our net force equation. Okay, so our net force equation was right here, and it said that the net force was equal to tension minus friction minus FGX. And so what we're going to do here is we're going to use this equation to solve for it. So first, let's find our FGX. Okay, so using this triangle over here, we know that my FGX is going to be opposite the angle. Okay, so for my FGX, it's just going to equal FG sine theta. Okay, so we know that. Now we know the tension, and we're going to do a substitution for this net force here. So if you remember Newton's second law, states that the acceleration of an object is equal to the net force divided by the mass. Now, if I rearrange this equation for the net force is equal to mass times acceleration. So what I can do here is I can substitute mass times acceleration in for this net force. And so if I rewrote that net force equation with that substitution, it would give me mass times acceleration is equal to tension minus friction minus FGX. And so looking at this, we can solve for FGX, okay, because we said it was FG sine theta. The problem gave me tension, it gave me the mass, and it gave me the acceleration. So we can rearrange this equation here and now solve for the friction. So to rearrange it, we're going to need to first add the friction over to the left side, and then we'll subtract the mass times acceleration to the other side. And so I'll kind of scroll this down here. That would give me your kinetic friction is going to equal tension minus FGX minus mass times acceleration. Now we can just plug in all our values. So our friction is going to equal tension, which we said our tension was 92 newtons, minus my FGX. So we'll plug in for the numbers for our FGX. Okay, so it's going to be 60 sine 30. Oh, sorry, sine 45. There we go. And then minus the mass of the object, which is 6 kilograms. And then the acceleration of the object, which was 5 meters per second squared. And now we can just plug in and solve. So if you plug all this in, your friction should equal 19.6 newtons. So kind of the takeaway here is sometimes we can use this Newton's second law and do some substitutions. Now let's go ahead and jump down to number 5. Okay, so we'll work this one together. So this one says we have a small child on a sled and it slides down a frictionless, I'm going to underline that, icy ramp which makes a 15-degree angle with the horizontal. Find the acceleration of the child on the sled. You do not need the mass. So let's first make our net force equation, or I'm sorry, our free body diagram. We have Fg down, and then we have the normal force, perpendicular. And so from here, this is all our forces, right? Because it's a frictionless icy ramp, so there's no friction, and they're just sliding down the ramp. So it's the x component of that weight that is causing it to, or the child to go down the ramp. And so if I make a net force equation from here, okay, so my net force and my x and my net force and my y. In the x direction, all we have is Fgx. And then in my y direction, we have our normal force minus my Fg, there we go, minus my Fgy, and that's equal to 0. So there's my two net force equations. And remember, the problem is telling me to find the acceleration. So we're going to focus on our net force equation in the x direction. And so remember, we can do some substitutions. So Newton's second law, like we did on that last problem, says the acceleration is net force divided by mass. So I can rearrange that. My net force is equal to mass times acceleration. So I can substitute in for the net force this mass times acceleration. And then for your FGX, let's kind of look at that. FG goes down, and then my FGX is right here. And here's the angle. So it's the opposite of our angle. So we would use our sine function. So your FGX would equal FG sine theta. So we can also do another substitution here, because remember, FG is equal to mg. And what I can do is I can plug in mg for your FG. So rewriting this, my FGX is going to equal mg sine theta. So now let's do all these substitutions. Okay, let's plug in mass times acceleration for your net force. And let's plug in this mg sine theta for my FGX. So if we did that, we would have mass times acceleration is equal to mg sine theta. And so if we look at it, both sides of our problem have mass. So that cancels out. And so that just leaves the acceleration, which is equal to g sine theta. And so now we can plug in. G will plug in 10 sine, and then your angle, which is 15 degrees. So this small child here has an acceleration of 2.6 meters per second squared. So when you're working through a problem, if you're looking at what they're asking you to do and you say, wait a minute, I don't have the mass, sometimes you don't need the mass. Okay, we can do some substitutions and cancel out that mass.